This project aims to investigate and define which materials would be used in constructions in a near future. As some of these materials are based on the ones that we have nowadays, we decide to include in this presentation the most common used materials now in order to understand the future materials. First of all, we're going to mention the popular materials of our days, which are cement, wood, metals, plastics, and clays. Then, we're going to explain which materials are going to be popular in the future. Cement is a fine mineral powder manufactured with very precise processes and the most used building material. Mixed with water, this powder transforms into a paste that bends and hardens when submerged in water. Because the composition and fineness of the powder may vary, cement has different properties depending upon its makeup. Common materials used to manufacture cement include limestone, shells, and chalk or marl combined with shale, clay, slate, blast furnace slag, silica sand, and iron ore. The manufacturing processes is the following. The raw ingredients are processed in cement manufacturing plants and heated to form a rock-hard substance, clinker, which is then ground into fine powder to be sold. Cement mixed with water causes a chemical reactions and form a paste that sets and hardens to bind different parts in constructions. It is used to make concrete as well as mortar and to secure the infrastructure by bending the building blocks. Concrete is made of cement, water, sand, and gravel mixed in definite proportions, whereas mortar consists of cement, water, and lime. These are both used to bind rocks, stones, bricks, and other pieces, fill or seal any gaps, and to make decorative objects. Cement mixed with water, silicates, and illuminates is used as a waterproofing material.
Wood has been used as a building material for thousands of years. This material is commonly used to build houses, shelters, and boats, but it is also used in the furniture and home decor industry as well. One of the biggest advantages of using wood as a building material is that it is a natural resource, making it available and economically feasible. It is remarkably strong in relation to its weight, and it provides good insulation from the cold. Wood is highly machinable and can be fabricated into all kinds of shapes and sizes to fit practically any construction needed. Wood is also the perfect example of an environmental sustainable product. Is it biodegradable and renewable and carries the lowest carbon footprint of any comparable building material. In addition, no high-energy fossil fuels are required to produce wood, unlike other common building materials such as brick, steel, or plastic. One type of wood commonly used in construction is known as engineered wood. It is the product of a more intricate fabrication process in which various wood strands, fibers, veneers, or other forms of wood are glued together to form a type of composite material that is used for specific construction applications. Engineered wood products are commonly used in a wide variety of residential, commercial, and industrial construction projects. Some benefits of wood in construction are that it's very resistant to high temperatures. It has a low heat conductivity. It has a highly sought after acoustic properties. It's resistant to electrical currents. It has a tensile strength, so it's able to bend under pressure without breaking, and is easy to fabricate.
Metals account for about 2/3 of all the elements and about 24% of the mass of the planet. Metals have useful properties including strength, ductility, high melting points, thermal and electrical conductivity, and toughness. From the periodic table, it can be seen that a large number of elements are classified as being a metal. Here are a few of the common metals and their typical uses. The key feature that distinguishes metals from non-metals is the bonding. Metallic materials have free electrons that are free to move easily from one atom to the next. The existence of these free electrons has a number of profound consequences for the properties of metallic materials. For example, metallic materials tend to be good electrical conductors because the free electrons can move around within the metal so freely.
Plastic is a material consisting of any of a wide range of synthetic or semi-synthetic organic compounds that are malleable and so can be molded into solid objects. The construction industry uses plastic for a wide range of applications because of its versatility, strength to weigh radio, durability, corrosion resistance. Plastic can be manufactured into forms such as pipes, cables, covering panels, films, sheets, and can be formed or expanded to create low-density materials and be dissolved into solvent or dispersed as emulsions. Some of the main types of plastic that are used in construction include acrylic, composites, expanded polystyrene, polycarbonate, polyethylene, polypropylene, and polyvinyl chloride. The advantages of using plastic in construction are that it's lightweight yet strong, which makes it easier to transport and move around sites. It is also resistant to rot and corrosion and has strong wearability due to it being capable of achieving tight seals. Plastic can also be flexible and is easily extruded. Bent, molded, 3D printed. Plastic can also be easily removed and some plastics can be recycled. The disadvantages of plastic are that it has high embodied energy content and a low modulus of elasticity, meaning that it's generally unsuitable for a low-bearing applications. Unless treated, most plastics are also flammable and have a high thermal expansion rate, which requires detailing to allow for adequate thermal movement.
Clay is a finely grained natural rock or soil material that combines one or more clay minerals with possible traces of quartz, metal oxides, and organic matter. Geologic clay deposits are mostly composed of phyllosilicates minerals containing variable amounts of water trapped in the mineral structure. Clays are plastic due to particle size and geometry as well as water content and become hard, brittle, and non-plastic upon drying or firing. Depending on the soil's contention which it is found, clay can appear in various colors from white to dull gray or brown to deep orange-red. Clay minerals typically form over a long period of time as a result of the gradual chemical weathering of rocks, usually silicate-bearing, by low concentrations of carbonic acid and other diluted solvents. These solvents, usually acidic, migrate through the weathering rock after leaching through upper weathered layers. In addition to the weathering process, some clay minerals are formed through hydrothermal activity. These are two types of clay deposits, primary and secondary. Primary clays form as residual deposits in soil and remain at the site of the formation. Secondary clays are clays that have been transported from their original location by water erosion and deposit in a new sedimentary deposit. Clay deposits are typically associated with very low energy depositional environments such as large lakes and marine basins.
Low-E glass has a microscopically thin, transparent coating that reflects long-wave infrared energy. Some low-E's also reflect significant amounts of short-wave solar infrared energy. When the interior head energy tries to escape to the colder outside during the winter, the low-E coating reflects the heat back to the inside, reducing the radiant head loss through the glass. The reverse happens during summer. There are actually two different types of low-E coatings: passive low-E coatings and solar control low-E coatings. Passive low-E coatings are designed to maximize solar heat gain into a home or building to create the effect of passive heating and reducing reliance on artificial heating. Solar control low-E coatings are designed to limit the amount of solar heat that passes into a home or building for the purpose of keeping buildings cooler and reducing energy consumption related to air conditioning. With this type of glass, we can save a lot of energy due to the properties of this special material. It's not only a question of innovation, this can be a revolutionary material in civil engineering, especially in the construction of buildings like offices or big residential zones. Graphene is a sheet of a single layer of carbon atoms. They are tightly bonded in an hexagonal honeycomb lattice. If layers of graphene are stacked on top of each other, they form graphite. Those layers are held together by van der Waals forces. Graphene is the tiniest compound known up to now. Also is the lightest and the strongest. Indeed, is between 100 and 300 times stronger than steel. Is one of the best thermal conductor and the best electric conductor man has ever tested. Bearing this in mind, one might be surprised to know that carbon is the second most abundant mass within the human body and the fourth most abundant element in the universe, after the hydrogen, helium, and oxygen. This makes carbon the chemical basis for all known life on Earth, so therefore, graphene could well be an ecologically friendly, sustainable solution for an almost limitless number of applications. The problem that prevented graphene from initially being able for developmental research in commercial uses was that the creation of high-quality graphene was a very expensive and complex process that involved the use of toxic chemicals, graphene as a monolayer, by exposing platinum, nickel, or titanium carbide to ethylene or benzene at high temperatures. The special phosphorescent cement is manufactured just like regular cement, though the researchers noted that the addition of phosphorescent materials does change the structure of finished product. As a result, this glowing cement will likely only be used as a coating material on top of other surfaces such as standard cements. By using additive, scientists are able to prevent the formation of crystals that occur normally during the production of cement, creating a material with non-crystalline structure that allows passage of light inside. Varying the proportion of additives added while manufacturing the cement regulates both its luminescent intensity and color. This can be really helpful in order to save energy. Instead of wasting our resources in lighting, we can build highways, streets, or pathways that are lighted by themselves.
Carbon fiber balsa is 3D printed. Balsa wood has a cellular architecture that minimizes its width since most of the space is empty and only the cell wall carries the load. It therefore has a high specific stiffness and strength. The direction that the fillers are deposited controls the strength of the material. This technique yields cellular composites that is as stiff as wood and twice as strong as the best printed polymer composites. The ability to control the alignment of the fillers means that this technique yields cellular composites that is as stiff as wood and twice as strong as the best printed polymer composites. The ability to control the alignment of the fillers means that fabricators can digitally integrate the composition, stiffness, and tautness of an object with its design. As we gain additional levels of control in filler alignment and learn how to better integrate that orientation into component design, we can further optimize component design and improve materials efficiency. 3D printing has the potential to radically change manufacturing in other ways too. Lewis says the next step will be to test the use of thermosetting resins to create different kinds of architectures, especially by exploring the technique of blending fillers and precisely aligning them. This could lead to advances not only in structural materials but also in conductive composites.
They take the form of cylindrical carbon molecules and have novel properties that make them potentially useful in a wide variety of fields. The diameter of a nanotube is on the order of a few nanometers, while they can be up to several millimeters in length. Carbon nanotubes are composed of carbon atoms linked in hexagonal shapes, with each carbon atom covalently bonded to 3 other carbon atoms. They are strong, not brittle, can be bent, and when released, they return to their original shape. They show high strength, unique electric properties, and high heat conductivity. These properties have caused researchers and companies to consider using them in several fields. For example, its highest strength compared to any other material has prompted researchers at NASA to combine carbon nanotubes with other materials into composites that can be used to build lightweight spacecraft. Carbon nanotubes can be found as multiple concentric cylinders of carbon atoms called multi-walled carbon nanotubes. Carbon nanotubes that have only one cylinder are called single-walled carbon nanotubes. Both main uses is to strengthen different materials. Its applications are used in a wide variety of sectors, not only in constructions. There are a few: electro field emission, thermal conductivity, energy storage, reinforcement of thermal materials, molecular electronics, structural applications in buildings, fibers and fabrics, biomedical applications, and avoiding air and water filtration.
Bamboo concrete. Bamboo reinforced concrete constructions follow same design, mixed proportion, and construction technique as used for steel reinforced. Just steel reinforcement is replaced with bamboo reinforcement. Even though existence of bamboo has been found from centuries, bamboo as reinforcement material is an innovation of the civil engineering construction field. This innovation was based on Clemson's study that has been conducted in the Clemson Agriculture College. The bamboo has a structure of a composite material with cellulose fibers aligned across the length. It has high, thick fibers near to the outer length of the bamboo, which is the main reason why they resist huge wind forces. The other important property is the tensile strength that bamboo has, compared with other materials including steel, which is the main requirement of a reinforcing material. The selection of bamboo for reinforcement can be done based on these factors: color and age, diameter, harvesting, and species. As bamboo is a natural product, it is more exposed to environmental agents and insects. A remedy against this is to undergo bamboo curing. The curing process enables the treatment of humidity content and the starch within it, which is the main reason for insect attraction. The curing is effective only if the chosen bamboo is right one. The curing of a bamboo can be done either by curing on the spot, immersion process, by heating, or smoke curing. The durability is a major concern for bamboo material. The physical and chemical properties of bamboo are found high with low content of humidity within it. This low content would keep away mold. Bamboo, being a natural building material, has the property of absorbing water, and this causes swelling of bamboo. Thus, concrete mixed proportion for bamboo reinforced concrete must have water cement ratio as low as possible. It should also be considered to use concrete with high early strength cement to minimize cracks caused by swelling of bamboo. Growing bricks. In 2012, U.S. architect Ginger Creek Dozier found Biomazon, a startup that aims to grow construction materials from organic matter. Dozier draws inspiration from a study of coral structure. Biomazon employs natural microorganisms to grow a durable cement at room temperature. The presence of bacteria in the bricks allows for hardening and the formation of biologically controlled cement, thus eliminating the bricking phase. In this way, CO2 emission and reliance on fossil fuel are reduced and materials can be produced on site. Traditional bricks, which are also made from sand and binding agents, have to be fired for 3 to 5 days, a process which generates approximately 800 million tons of carbon emission each year. Biomazon's BioBrick takes only 2 or 3 days to grow and eliminates the emission altogether. What's more, Dozier says her company's bricks can even absorb pollution, making them an active agent in the war against climate change. By replacing traditional bricks with a grow version, Biomazon aims to make a dent in the enormous carbon dioxide emission produced by the construction industry, which accounts for around 40% of global emission. In the process created by Biomazon, sand is mixed into a wood mold with bacteria, which are fed with a water solution and calcium ions. This enables the brick to harden without using kilns, where they are normally kept for 3 to 5 days.
Engineered cementitious composite, also called strain-hardening cement-based composites, or more popularly as bendable concrete, is an easily molded mortar-based composite reinforced with specially selected short random fibers, usually polymer fibers. Unlike regular concrete, ECC has a strain capacity in the range of 3 to 7% compared to the 0.0% for ordinary Portland cement (OPC) based mortar or concrete. ECC therefore acts more like a ductile metal-like material rather than a brittle glass-like material as those OPC concrete, leading to a wide variety of applications. ECC, unlike common fiber reinforced concrete, is a family of micro-mechanically designed materials. As long as cementitious material is designed and developed based on micromechanics and fracture mechanics theory to feature large tensile ductility, it can be called an ECC. Therefore, ECC is not a fixed material design, but a broad range of topics under different stages of research, development, and implementations. The ECC material family is expanding. The development of an individual mixed design of ECC requires special efforts by systematically engineering of the material at micro, macro, and composite scales. ECC looks similar to ordinary Portland cement-based concrete except that it can deform or bend under strain. Traditional concrete lack of durability and failure under strain, both stemming from brittle behavior, have been a pushing factor in the development of ECC. Thermochromic cement. Smart materials, called also intelligent or responsive materials, are design materials that have one or more properties that can be significantly changed in a controlled fashion by external stimuli, such as stress, temperature, moisture, pH, electric or magnetic fields, light, or chemical compounds. Smart materials are the basis of many applications, including sensors and actuators, or artificial muscles, particularly as electroactive polymers. Terms used to describe smart materials include shape memory materials and shape memory technology. The applications are based in the obtention of data and auto-analysis of the inner conditions of the material, so they are basically used to regulate the temperature of the walls.
Aerogel is an opal cell that contains pore ranging from 2 to 50 nanometers in diameter, solid foam that is composed of a network of interconnected nanostructures and exhibits a porosity, non-solid volume, of no less than 50%. The term aerogel doesn't refer to a particular substance, but rather to a geometry which a substance can take on, the same way a sculpture can be made out of clay, plastic, papier mâche, etc. Aerogels can be made of a wide variety of substances including silica, most of the transition metal oxides, most of the lengthy and alkaline metal oxides, several main group metal oxides, organic polymers, biological polymers, semiconductor nanostructures, carbon nanotubes, and metals. The unique combination of properties makes aerogels useful in a range of applications and best candidates for many others in the future. Aerogels can be used for thermal insulation, supercapacitors, water deionizers, sensors of gas detections, pollution filters, the electric coupling layers integrating circuits, absorbent for desiccation, insecticides, dangerous liquid storage vessels, catalysts, matching layers for acoustic transducers, sound insulations, kinetic energy bound absorbers, sound insulations, impact protections, crucibles for molten metals, nuclear particle detections, and many more.
Hey Jude, don't make it bad. Take a sad song and make it better. Remember to let her into your heart. Then you can start to make it better.